Welcome back, everyone. Over the weekend, I received a few questions by email about the programming exercise that is due on Tuesday this week. So what I decided to do was to post some additional suggestions on the course website about how to approach that problem. So now if you go to the programming assignments portion of the website and click on the exercise that's due on Tuesday, you'll see that what I've done is I've posted some additional suggestions about how to best approach the problem. So that's the first thing I want to take you through today is just want to talk about some of the things that I posted here and explain some of the suggestions for how to approach this particular problem. Let me arrange things on the screen here. All right, so to start with, what we're doing in this problem is we are computing a sum of a collection of terms. And the purpose of computing this sum is to generate an estimate for pi. That also serves to give you a very nice built-in way to tell whether or not you're on the right track, because if you compute this sum correctly, you should be producing an estimate which is very close to pi, about 3.14, so on and so forth. All right, now let's go through the mechanics of computing a sum like this. Now, I've already shown in an earlier example from the lecture how you typically approach computing a sum like this. So let's go back to that earlier example and see some of the key features of how you would approach a problem of computing a sum. Right, so in that earlier example, I was computing a simpler sum than the sum that we have to compute, but nonetheless, these two problems have a lot of features in common. The first thing for you to pay attention to from that previous example is the general structure of how you go about successfully computing a sum of a collection of terms. The obvious ingredient here is you're going to need some sort of a while loop because you have many terms that need to be generated and added up, and using a loop is the obvious way to automate the process of computing those terms and adding them all up. Right now, in any loop that you write, there's going to be a loop counter variable. So in problems where you're computing a sum, the usual arrangement is you have a loop counter variable named n, and that starts out at 1, and it goes for however many terms that you want to compute. And the idea that you should have in your mind is that each of the terms that makes up the sum is numbered. All right, so this is term number 1, term number 2, term number 3, and so on. And the last term that we're computing in this example is term number I, where I is some number that's going to be determined in some way. Right, so that sets up the main structure for the loop. You have a loop counter variable that starts at 1. The loop runs as long as n, and this should actually be less than or equal to. That's a little mistake there. And then on each trip to the loop, the last thing you do is you increase the loop counter variable by 1. Right, now the next thing beyond the basic structure of the loop is the fact that we're computing a sum. So another ingredient that you're going to need here is you're going to need a sum variable. And the obvious purpose of this variable is this basically is where you're going to be storing the running total as you start adding things up. The obvious way to start that summation is to start it with a value of 0, because before you've seen any terms and you've added anything to the sum, that's the obvious starting point for your sum. Then a third variable that you're going to need in this calculation is a variable that you use to store the value of the individual terms in the sum. Then given all of this, the basic action in the loop is that on each trip to the loop, the first thing we're going to do is we're going to be computing the next term in the sum. And then once we've computed that term, we're going to be adding it on to our running total by doing this statement here. Right now, the only thing that I have sort of left undetermined in this code is exactly what happens when it comes time to compute one of the terms in the sum. And the reason that I left that unspecified is that this is the main thing that's going to change from one example to another. Right, so for example, when we're computing this sum, the rule for computing the individual terms will look different than the rule for computing the individual terms in this sum. Right, so that part of the code will vary from one example to another as the nature of the terms themselves change from one example to another. All right, and finally, one last thing that I showed on this slide here is that you have an option for how to write the loop. This all depends on what you're more comfortable doing. If you're most comfortable using a while loop, then by all means use this form. If you want to instead use the for loop, here's the equivalent thing written out as a for loop. Right? But in either case, the main thing going on is that on each trip through the loop, we have to compute a new term and we have to add it to the running total that we are generating. Okay, now finally, let's tackle the question of what should happen here when it comes time to compute an individual term. The main thing for you to think about here, again, is this idea that what we're doing is we are numbering the individual terms. So this is term 1, term 2, term 3, and so on. And you're going to follow that same procedure in any sum that you do. So in this example, this would be term 1. This is term 2. This is term 3. All right, and again, the thing that is labeling those terms is the loop counter variable. As the loop runs, the counter variable runs through a range of values starting at 1, going all the way up to the largest value. And on each trip through the loop, you'll have at your disposal the current value of that loop counter. So for example, if we're working on this term, that's the 4th term. So at that point, n would equal 4. Right, now, the main thing that you need to figure out is what is the relationship between the loop counter variable and the terms that you're constructing. All right, so let's look at an easier example first. So here's the easy example. And in the easy example, it's very easy to see what the relationship is between the loop counter variable and the individual terms. In fact, if you want to be very, very careful and systematic about this, what you might do is write out a few examples of the loop counter variable and the associated term and look to see if you find a pattern, and that pattern determines how the terms are generated from the loop counter variable. All right, so again, in this first basic example, that relationship is very simple. Each term is basically 1 divided by the current value of the loop counter variable. All right, so in the first basic example, this is how you would construct the individual terms. Each term is based on the current value of the counter variable, and you get each term basically by taking 1 divided by the counter variable. And the only other thing to watch out for here, and this is a thing where there's the potential of making a simple mistake. If you try writing this out as simply 1 divided by n, you're going to run into a problem caused by the fact that this counter variable is usually an integer variable. And if that counter variable is an integer variable, and if you put an integer 1 in the numerator, what that's going to trigger is integer division. And the problem with integer division is that if you take 1 and divide it by n, in almost every case, it's going to be 0. That's going to zero out almost all of your terms, which is the wrong thing to do. All right, so the fix for that is when you're especially when you're doing a division, make sure that at least one part of what you're computing does not look like an integer. So here we fix that by making the numerator look like a floating point number. As soon as at least one of the two numbers in the division is not an integer, you don't get integer division, you get ordinary division, and it starts producing the results that you expect to see, and the summation works correctly the way that it should. Okay, so now, again, in the homework exercise, you're not going to be dealing with this simple summation. You're going to be dealing with something a little bit more complex. So let's look at how you would map the counter variable to the term in the case of the more complicated summation. But before I do that, Mark has a question. Would you like to ask your question quickly?
Yeah, quickly. What's a counter variable by definition?
Well, again, a counter variable is what you have in a loop when you use some sort of variable to control how many times you've gone around the loop. Right? That variable, in this case, it's the variable n. We commonly refer to that as a loop counter variable. And almost every loop has something like that, a variable that counts how many times you've gone around and controls how long and how many times the loop goes around. That's a counter variable.
Thank you.
Okay, and almost every loop that you write is going to have a counter variable. And in almost every loop, there is going to be something you're computing. And very often the question you come across is, how is the thing you're computing related to the counter variable? Again, in the example of this simple sum here, the relationship is that each term you're computing gets computed from the counter variable by doing something like this. Now, in the homework assignment, the relationship between the counter variable and the terms is going to be a little bit more complicated. And again, to help you see what that relationship is, I've written out the first few examples. On the left are different values for the counter variable, and on the right are the corresponding terms that you need to be generating for each of those different values for the counter variable. Okay, now your assignment in this homework assignment is to figure out what this relationship is. What is the connection between the counter variable n and the corresponding term that you're computing? There's a formula that you can write down that expresses the correct relationship between these two things, and that is the formula that you will use to compute the individual terms in sum. Right. Now, one other complication in this example is you have another special feature in this example, and that is the alternating signs. For the first term, we have a positive term. For the second one, it's negative. Third is positive. Fourth is negative, and so on and so forth. And for every other term after that, the signs alternate. Okay? Now, you'll have to come up with some sort of a strategy that generates the right sign for each term. I can think of at least 3 different ways to do this, so I'll leave it up to you to come up with at least one way to successfully figure out how to get the right sign for each of these terms, and that's going to be another thing that you'll be thinking about when you write out the expression for the individual terms. Okay, so again, to make a long story short, what you're going to be doing is you're going to be writing a loop that looks either like this while loop or like this for loop. And the missing ingredient in both of these cases is the rule for how to compute the terms. And to figure out how to compute the terms, you take a look at this table and ask yourself, what is the connection between the counter variable n and the term that I need to generate? That's going to lead to a formula for that term, and that formula is what you're going to be putting in place of the question marks in the code here. Okay, so that's an overview of what you're going to be doing to compute the sum. Now, there's one last aspect of this program, and that is for this program, you're not going to be computing just one sum for one value of I. You're actually going to be computing several different sums. So another thing that you're going to need is you're going to need to take the code that you have written to compute the sum and put it inside yet another loop. All right, and here's what that loop would look like. The purpose of this loop is to cycle through different values of I. What this loop is going to do is it's going to start out with I equals 10,000. It's going to do a series of different values of I, and on each round, the value of I is going to go up by 10,000. So we're going to go 10,000, 20,000, 30,000, and so on, all the way up to 100,000. And for each different value of I, what you're going to be doing is you're going to take the code that you wrote to compute the sum. You're going to stick that code in here in place of this first comment to actually compute the sum. And then after you've computed the sum, you're going to be printing both the current value of I and the sum that you just computed. And you're basically going to end up printing a table. And what this table will be showing you is for each of the different values of I, it will be showing you the corresponding estimate that goes along with that. And you can see how the estimates change as you make the I grow larger and larger. All right, so in this exercise, you're actually going to have 2 loops. There's an outer loop that goes through different values of I, and there's the inner loop that computes the sum for each different value of I, and that's the overall structure of what you're going to be doing. Okay, any final questions about what I've posted here and how to approach the problem? Okay, if not, don't forget, I just discovered a mistake in the code. The mistake is that in both this while loop and in this for loop, this should be less than or equal to. After the lecture, I'll be fixing that mistake online, so eventually that will get patched up on the course website. Okay, now the next order of business today is to pick up where we left off last time. And last time I was beginning to introduce you to the concept of working with files. So let's begin by bringing up an example that I showed at the end of the class last time. Now, again, this material is an extension of the material on loops because we're still talking about processing things with loops. The only difference this time around is that for these examples, we're also going to be working with a file. And the first example that we looked at the end of the lecture on Friday was an example that uses a loop to systematically read every number from an input file and then print those numbers out to the output pane. Right? And again, just a quick review of what's going on here. The first new idea that I showed you in the example was that when you're reading from a file instead of from the console, you have a slightly different procedure for setting up the scanner. In this case, instead of having the scanner read from system in, we're going to set up a scanner that instead reads from a file. And an unfortunate complication when you do that is when you start working with files, you have to deal with exceptions. And that requires us to layer more code around this. We basically have to set up what's called a try-catch block. This is basically a thing that handles something going wrong with the file. And if something does go wrong, what we're going to do is we're going to simply print an error message saying, sorry, I wasn't able to open the file. And then we go ahead and exit the program. All of this garbage is stuff that you need in cases where you're reading from a file. But the good news is that you can simply copy and paste from this example to other examples so that anytime you need to open a file and read from it, you can simply paste in this blob of code, and that will do the job for you of setting up a scanner that reads from the file. All right, and then also in the example last time, I showed you another special feature that you get when you're working with a scanner that reads stuff from a file is this method here. This is an example of what's called a has-next method. These are methods in the scanner class whereby you can ask the scanner, do you have more data for me? Do you have another integer that I need to work with? And you can use that as a tool to control a loop. In this case, we've set up a while loop that basically says, while the scanner still has more numbers left for us to work with, we're going to take another trip around the loop. All right, then on each trip through the loop, we're going to use the scanner in the usual way to read an integer. The only difference this time, instead of having the user type in the integer for us, the integer is going to be pulled out of the file. And then for each integer that we read, we're going to do something with it. And in this first basic example, all we're going to do is just print that integer directly to the output. So you can see that the integers have been read successfully from the file. Okay, now one final ingredient that we need here is the text file itself. For this example to work correctly, we have to have set up a text file named numbers.txt, and that file needs to have numbers in it. All right, now, one aspect of working with this that you might find a little bit confusing is that when you're working with a project that has code that works with the text file, the somewhat confusing thing is that you won't be able to see the text file itself directly. What you need to do to see that is switch to a different view. Instead of the usual projects view, what you can do is click on the next tab over, which is the files view. And in the files view, that will show you the contents of your project. And one of the things that will show you is it will also show you any text files that are in that same project. All right, so when we switch over to the files view and we look at this particular project, you'll see that inside this project, there is in fact a text file named numbers.txt. And if you want to take a look at that, you simply double click it, and that will show you the contents of that particular text file. All right, so that's how to actually find the text file and examine it when you are working with a project that has a text file in it. Okay, now let's put away that first basic example and switch to a second example that I brought along today. In that first example, the processing that we did on the data in the file was pretty minimal. For the next example, what I want to show you is a more typical example where we are reading a bunch of numbers from a file for the purpose of answering a question or doing some sort of more sophisticated processing on the data that comes in from the file. Okay, now, once again, we're going to be dealing with the same text file as before, and that text file contains a list of numbers. These numbers are in no particular order, and the numbers cover a range of values. Right. Now, the question that I would like to answer in this next example program is, what is the smallest number in the file, and what is the largest number in the file. Okay, now in a simple case like this, we could answer that question ourselves just by looking at the file quickly. Here you can see clearly that the smallest number is 1 and the largest number is 7. But that gets harder and harder to do as the text file gets more and more complicated. Imagine instead a file that contains 1,000,000 numbers, and each of these numbers is typically a very large number, something like 2,652,345. In that case, it becomes a lot harder just to eyeball the numbers in the file and answer the question, which is the smallest number and which is the largest. And when the data set gets that big and complicated, we'll need a program to answer that question for us. Right? So that's what's going to be going on in the example. We're going to write a program that can read an arbitrarily large data file and answer the question, what is the smallest number in that file and what is the largest number in that file? Okay, so first off, to do this, the first thing we'll need is, just as in the previous example, we'll need this typical block of code that is responsible for opening the file and getting ready to read the contents of the file. All right, and just like the last example, the actual reading is going to be taking place in a while loop. It's going to be set up the same as the last example. As long as there are numbers still available, we're going to be reading those numbers and then processing those numbers as they come in one by one. Okay, now the new feature in this example is that in this example, we have a job to do, and that job is to answer the question, what is the smallest number in the file and what is the largest number in the file? So we're going to need to add some extra logic to this to answer that question. All right, so the starting point for this is to set up a couple of variables. I'm going to set up one variable called smallest and another variable named largest. And this is where we're going to be storing both the smallest number we've seen so far and the largest number that we've seen so far. Okay, now an important consideration anytime that you set up a variable is you always have to give your variables a suitable starting value. And an obvious way to do that in this case is we're going to go ahead and read the very first number that's in the file. And as soon as that first number comes in, it automatically becomes both the smallest number we've seen so far and the largest number we've seen so far, because it is the only number that we've seen so far. All right, so that's an obvious way to initialize both of these variables. We read a number that automatically becomes the smallest number, and then that smallest number we've seen also is the largest number we've seen. So that is a logical way to initialize both of those variables. All right, then the final part to talk about here is what happens in the loop. All right, now on each trip through the loop, what we're going to be doing is we're going to be reading a new number from the file, and as each new number comes in, we might want to reconsider which is the smallest and which is the largest, and we can do that with a couple of simple if statements. The first if statement takes a look at the new number and asks, is it smaller than the smallest thing I've seen so far? And if it is, it gets to become the new smallest value. Right? And likewise, if the number that we just read is larger than the largest thing we've seen so far, it gets to become the new largest value. Right? And by systematically doing those tests for every single number we read, eventually, after we've read every number in the file, we will have found the smallest number in the file and the largest number in the file. All right, so let's pause here and ask for questions.
I got a question.
Mm-hmm.
I just noticed on lines like 22 and 24, you have an if without an else. So does the program then, it just ignores, like if you have an if without an else, it only does something if the if statement is true, and otherwise it just continues as normal?
Right, exactly. This is one of the special features of if-else statements is that the else part is optional. So if you have a situation where if you're checking to see if something is happening and you want to do something if that thing happens, but you want to do nothing if that thing isn't happening, this is the right construction you'd use. You basically would leave off the else part. So that basically is saying, for example, if the number you just read is not smaller than the smallest number, you simply want to do nothing. You just want to leave it alone.
Cool.
Okay, now, was there another question here? Okay, so That then handles the logic. And again, the whole purpose of a loop is to do this for every single number in the file. And once we fall out of the loop, we have processed every number that's in the file, and we hopefully will then have found the smallest and the largest number. Right now, one final thing we need to do when the loop is finished, and this is a thing you want to get in the habit of doing when you're working with files, and that is a special feature of files, is when you're done working with a particular file, you should close that file and put it away. And the way you do that is by using the close command on the scanner, telling the scanner to close will close both the scanner and the file that it's reading from. And this is a thing that you typically need to do when you're working with files. All right, and then of course, the last thing for this example to do is to actually print the results and print both the smallest and the largest number in the file, and that's what the print statement does. So again, finally, just to check that this works, let's run it and see that it does find that the smallest number in our file is 1 and the largest number is 7. Right, and that's exactly the thing it does, and it works correctly. Okay, so that is a more typical example where we are reading a file for the purpose of doing something with the data that's in the file. And for that, we need to add extra logic to our while loops that processes each number that comes in to help us answer some question that we're trying to answer. All right, so that is the find smallest and largest example. Okay, now I brought along one last example of working with files today. And in the last example, we're not going to be reading to a file. We're instead going to be writing information to a file. Now, unfortunately, that requires a little bit different setup. So for this example, we have to set things up in a slightly different way. Okay, now, in any situation where your goal is to write data out to a file, what you're going to be doing is similar to what you would normally do to produce output in a program. Up until this point, anytime we wanted to produce output in a program, the way we would do it is we would be using print commands. So we would be typing things like system.out.print, and that was the mechanism whereby we showed output to the user. Right now, in this case, instead of printing our output to the output pane by using system.out, we're going to be using a different mechanism, and that mechanism is a thing called a print writer. Right. Now, the purpose of the print writer is to make it possible for us to print our output to a file instead of printing our output to the output pane. Right. And here are the basics of how you use a print writer. So first of all, a print writer is a new class, and to use it, there has to be an import statement that goes along with it. So in this case, we have to import the print writer class to make use of that. Then the second step is to set up the print writer. We set up the print writer similarly to the way that you would set up a scanner. Again, what we're going to be doing in this case is we're going to be pointing that print writer at a file and telling it any output that you produce is going to be sent to that file. Right, so here we have to provide a name for the file that we are sending the output to, and then anything that we print to that print writer is going to get sent to that file instead of being shown in the output pane. All right, and then the last thing you need to know about the print writer is that the print writer makes it possible for you to print things. Right, and in that case, the print statements look very similar to what you're used to doing. The only difference is instead of saying system.out.println, what we're going to be saying instead in this case is we're going to be talking to the print writer variable. And we're going to be saying to the print writer, here, print this stuff for me. And anything that you ask the print writer to print is going to get printed out to the file, and it will get saved into the file. Right? So that gives us a basic mechanism for dumping stuff into a file. We simply do a bunch of print statements, and anything we print will get sent out to the file instead of being sent to the output pane. Okay, and then finally, to get this example to actually do something interesting, what I've done is I've stolen one of the earlier examples from the loop lecture. What I did is I took an earlier example that goes through and finds all of the prime numbers from 1 to 1,000. That previous example printed all of those numbers to the output pane. The only difference this time around is I'm going to be sending those numbers out to the print writer, and they're going to go out to the file instead. Right. And finally, the last thing to do here is because we are dealing with a print writer that is working with a file, An important step to do at the very end is when we're done printing stuff out to the file, we have to close the print writer. That will close the print writer and then close the file that we are working with. Now, in this case, the close statement is even more important than it usually is, because if you accidentally leave off the close statement, what will happen is when you run the program and then you go and take a look at what's in the file, you may be surprised to see that there's actually nothing in the file. Right? Now, the reason that happened is that one of the things that print writers do is when you ask them to print a bunch of data, in many cases, they won't send that data out to the file right away. Instead, what they're going to do is they're going to sort of make a local copy of that data and hang on to it. And something that will cause the print writer to actually send the stuff out to the file is the close command. As soon as you give the close command, if the print writer was hanging on to something that it hasn't yet sent to the file, as soon as you issue the close command, all of that stuff will get sent out to the file, and you'll actually have something in your file that gets written, right? Again, this is very surprising, because if you accidentally leave off the close command, you'll open up the file in many cases and find that it's completely empty. To fix that, you have to put the close command in at the end of what you're doing. All right, and once again, to find the file that you have written stuff to, creating the file is just as simple as doing this. If you want to actually see what's in that file, what you do is you go back to the Files view, excuse me, and then in the Files view, you'll be able to actually see that file, and then you can open it up. Here, I've already run the program, and you can see that in the file, we have all of the prime numbers that the program generated exactly as we expected. All right, so that's how you actually locate the file to open it. You have to go to the Files view instead to find that file and open it and see what's in it. Okay, so those are the file examples that I wanted to cover today. Any final questions about any of those three file examples? Okay, now if not, we have about close to 15 minutes left, so I want to take advantage of the time that we have left and move on to the next set of material in the course. So let me put away the project with the file examples in it, and let's move on to a project that shows us some examples for the next topic that we're going to cover. Okay, so the next topic that we're going to cover is the topic of writing your own methods. And you'll find coverage of this topic in chapter 6 in the textbook. That'll be the next chapter for us to move into. And let me start by showing you one of the first examples that shows up in chapter 6. Now, this is a somewhat artificial example. The main purpose of this example is to give us an excuse to talk about methods, which is what we're going to be talking about in chapter 6. Okay, now what we see in this example is several examples of loops. And what each of these loops are doing is that they're computing sums. What they're doing is they're basically taking a range of integers and then adding up all of the integers in that range. The first range runs from 1 to 10, and the first sum computes the sum of those things. Then we repeat that experiment with slightly different ranges. The next experiment is to take the numbers in the range from 20 to 37 and add all of them up and see what that sum is. And the final experiment is to try with a third range, where we have the numbers in the range from 35 to 49. Okay, now again, this example is a little bit artificial. It doesn't answer the question of why we're computing these sums. This example is just here purely for the purpose of being an example. And the main thing that we want to talk about in this example is that what we're doing here is we're doing three very similar things. Okay, now one obvious way to handle a situation like this is if you have three tasks to do that are very similar, you can do these three tasks basically by doing a copy and paste procedure. What you do is you write out the code for the first sum that needs computing, and then once you've solved that problem for the first sum, to solve that problem for the other ranges, all you would simply do is copy the first block of code, paste a copy of that into your code, and then make a few small changes to that copy. So the only change we would make in the copy is we would change the numbers that we use for the range, right? So by doing multiple examples of this program, all we would do is solve it once and then copy that code and paste in a couple of copies and then modify each of those copies to have each copy do exactly what we want it to do. All right, so that's one way to approach this, basically by using a copy and paste strategy. Okay, now the next thing to say about this example program is because it's doing three things that look very similar, one criticism you can make about this code is that it's somewhat redundant, because what we have here is three blocks of code that look almost exactly the same. The only small difference in each block is the actual range of numbers that we're working with. Okay, now redundancy is something that experienced programmers don't like to see in their programs. Once you move beyond the sort of introductory level of learning to program, and as you get to be a more and more experienced programmer, one of the things that experienced programmers don't like is precisely this type of redundancy, where you have three blocks of code that are doing almost exactly the same thing. And one of the reasons that programmers don't like this type of redundancy is that, especially if you have very large blocks of code that are being copied and repeated, that starts to take up more and more space, right? And if there's one of the things that experienced programmers don't like is code that's very wasteful of space. Because if you have code that takes up a lot of unnecessary space, that makes it harder to see other parts of your program. So a real bias that's built in among experienced programmers is, as much as possible, they want to make their code as short as possible, so that that saves space and makes it possible for them to see more things at once when they're looking at their code. Right? So that's why experienced programmers don't like redundancy, because redundant code is not very space efficient code, and they want to instead switch to a form that's makes more efficient use of space. Okay, so that's the motivation behind this example. That's the criticism we can make about this code, is that it's redundant and therefore wasteful of space. And that's going to motivate us to find a way to do this much more efficiently. Okay, now next, I'm going to bring up a piece of code that does all of this more efficiently. And the mechanism that it will use to do this more efficiently is the use of a method. Okay, so here is the second version of the code. And the main thing that the second version does is it takes all of the code that used to be in main and shrinks it down so it takes up only 3 lines of code. In the previous version, the code that we had in main covers more than 3 lines of code. It runs from line 5 down to line 22. That's a total of 17 lines of code. So if we can successfully shrink 17 lines of code down to 3, that's a win. Okay, now what makes it possible to shrink our code that dramatically in main is what we've really done here is we've taken some of the work that main used to do, and we've moved that work to a different place. And what we've done here is we've created an example of a method. So the first new thing going on in this example is that for the first time in this example, we're going to be seeing how to create our own methods and how to successfully use those methods in our code. Okay, now this is going to take a few minutes for me to sort of dig through the details of this example, because there's a lot of stuff that goes into creating a method. So bear with me for the next 5 minutes or so as I take you through the mechanics of setting up and using your own method. Okay, now the first thing to say about this is that a purpose of a method is that a method is meant to compute something. And the first thing that you'll do when you set up a method is you'll need to name that method, and you'll need to give it a name that reflects what the method is actually doing. All right, so in this example, what we're doing is we're computing a sum, so that becomes a natural candidate for the name of the method. All right, so this is where the name of the method appears in the overall structure. Now, the next thing that goes on here is that most methods typically work with one or more inputs, and they produce one or more outputs. Right? Now, in the case of the inputs, those are the additional pieces of information the method will need to do its job. In this case, the inputs are in the form of what we call parameters, and the parameters show up in the method right after the name of the method. Okay, now the parameters basically function as a way for us to give the method two inputs, because in this case, what we're going to be computing is we're going to be computing the sum of a range of numbers, and to do that sum successfully, we need to know what that range is. Right, so to describe what the range is, we need a couple of variables. These variables are called I1 and I2. And these variables are set up as what are known as parameters. These are special variables that play a role in the method. They basically give us a way to give inputs to the method, and we set up those inputs by setting up a couple of variables that serve as parameters. And the parameters in the method, they show up right after the name of the method. Okay, now once we have specified what the parameters are, we can actually start thinking about using the method, because to use a method, all you need to know is you need to know what its name is, and you need to know what inputs the method is going to expect to receive. All right, and in this example, the method is named sum, and the two inputs it's expecting to see are the beginning and the end of the range that we want to add up. Right? So if we want to actually use this method, we'd invoke it by doing something like this. We basically say, okay, I'd like to use the sum method, and each time we use it, we need to give it a range to work with. Right? So in the first example, we're saying, I'd like to sum up all the numbers from 1 to 10. In the next example, we're instead saying, I'd like to sum up all the numbers from 20 to 37. And in the third example, we're saying, I'd like to sum up all the numbers from 35 to 49. Right? And by simply invoking this method with different ranges, we can get the same method to solve the same problem 3 different ways by giving it 3 different sets of inputs. And in each case, when we invoke this method, what's going to happen is that the first number that we specify here is going to get placed into this variable, and the second number that we specify is going to get placed into this variable. And at that point, the method will have all the inputs that it needs, and it will then go ahead and do the calculation for us. All right, so what happens next is once we've specified what values to use for the inputs, we'll go up to the sum method and we'll enter the body of that method, and we'll start running the code that appears there. Right, so now at this point, we know everything we need to know to do the job. We know that what we're supposed to be doing is we're supposed to be computing a sum. We know that this sum is the sum over a range, and we have specified what that range is because somebody has told us what values to use for I1 and I2. Right, so now we can go ahead and we can compute the sum, and then the very last thing that needs to happen when the sum is done is we need to do what's called returning the output of the method. All right, especially if the method is designed to compute something, there has to be a way of saying, okay, here's the answer that I just computed. And the way that you do that in a method is the very last thing you do is you write what's called a return statement and say, hey, here's the value I just computed for you. I'm going to return that value to you so you can then do something with it. Right, so then down here in the code where we call the method, once we specify what inputs the methods will work with, the method will do its job, it will produce a result, and then as soon as the method will produce a result, we're going to do something with that result. In this case, we're going to be printing it. So when the result comes back out of the method, we're going to grab that result and tack it onto some text, and then we're going to print all of that text, and that's how we use the result of the method. Okay, and one final bit of structure that you need to set up the method successfully is that if you're going to be returning a value from the method, as part of setting up the method in the first place, you have to specify what's called the return type, and that shows up right here. In this case, the result that we're generating and returning is an integer, so when we're setting up the method, we need to say that the return type of this method is an integer. Right? And these two things have to be consistent with each other. If you say that this method is going to return an integer and you instead end up returning that something that looks like a double, for example, if I tried returning an actual number here, that would immediately get flagged as an error. And if you look at the error message, it would say again, incompatible types. And the reason that these are incompatible is that up here, I said this method will be returning an integer. Yet when I actually get to the return statement, I return something that is not an integer, and that causes Java to complain, right? And again, the fix for that is to make sure that whatever you're returning has a type that matches what I said up here, right? So this will advertise the fact that this method takes a couple of inputs and computes something, and the thing it's computing that's going to come back to you will be an integer. All right, and then the last thing that you need to successfully set up a method is you need to start the method with these two keywords. And in all of the examples that we're going to be looking at for a while, all of these methods will start with the words public and static. For the time being, all I'm going to say is that all our methods need to look like this, and it will take a while. It will take us until chapter 10 before we see examples where methods don't start with public or static. But for the time being, I'm just going to say that all methods have to start this way, and eventually I'll explain how you could potentially do that differently. Okay, so we've got some questions here, so let's pause and ask for questions quickly here.
Oh yeah. Can you explain again why we need to have that return statement?
Okay, the purpose of the return statement is that in most cases, the purpose of a method is to compute something. And what you need is some way to get the answer you've just computed out of the method. And that's what return statements do. Usually return statements show up at the very end of the method, and their purpose in life is to take whatever you've just computed and make sure that that value makes its way out of the method. Because if the method is designed to produce some sort of an output, you generate that output through a return statement.
Thank you.
All right, any other questions at this point? Okay, so at this point, we are out of time. We've only had enough time today to just begin to scratch the surface on the whole topic of methods. So come back on Wednesday, and on Wednesday, all day throughout the entire lecture, we'll be seeing lots more examples of methods. And over the course of many examples, you'll get a much better sense of how to set up a method, why to use methods, and how to use them in your program, right? So stay tuned until Wednesday for lots more examples about methods.